Hello, and welcome back if you just watched my two previous videos. If you didn't watch those videos, go watch them now, otherwise you won't be able to understand what I'm talking about. And if you read the title carefully, you might have noticed that the title is very different this time. This time it's Homemade YouTube Coriolis Mass Flowmeter Sensor, which is a great match for the website on which you are watching this video. Get it? YouTube for YouTube. Okay, it's a bit cringe, but anyways, let's get started. In the previous two videos, I was using a straight pipe, which is the one at the bottom left corner. But this time we're going to use a U-shaped one, which is in the red box. And I must confess that the process had not been an easy one. We even bought a special tool to help us bend the tube, but because the tubes that we are using are very thin, we specially chose thin tubes because they will have very little impact on the data that we get. But because they are thin, the tubes are very easy to bend, or too easy perhaps, because usually they just bend over sharply, and this picture shows how many tubes have been wasted during the process. But in the end, I found a much better way, and here's how we did it. Well, it might not be very scientific, but it's definitely homely. Do you remember that in the last video I talked about a speaker with a magnet in its outer structure so that it can be stuck on a metal plate? Well, this time I found something new. It's called the bone conduction speaker, and actually I don't care about how it conducts sound. Only thing I care about is that it has a very large slit. So, as you can see in the picture, the slit is definitely large enough, so this one definitely get a yes. Well, this is what our newly made YouTube Coriolis Mass Flowmeter sensor looks like, and here's some data about it. Then I tried to find the resonance frequency, and it turned out to be 57.1, which is, well, much lower than the previous ones. After that, just like last time, I did some knocking. And some pressing. Which both turned out to be fine, and a lot better than the last time. And then I filled it with water, and so the resonance frequency changed from 57.1 Hz to 53.87 Hz. Next, I started to measure the signal from the driver and the sensors. Finally, I'm able to use those components that I mentioned in my first video and yet never used until 2 videos later. This is a screenshot from the interface of our data acquisition module. And as I said in my first video, there are 8 channels, and yet we are only using 3 channels. 1 for driver and 2 for sensors. And I'm measuring a total of 500,000 of cycles, and each cycle has a period of 10 microseconds, which means we are actually measuring for a total of 5 seconds. And for the graph, the one signal with a lower magnitude is the signal to the driver, and the other 2 with a higher magnitude are signals from the sensors. Here's a much more compact version of the previous graph. And here's the structure that we built in order to produce water flow. We used a pump, which is the black thing in the middle, and it is powered by DC voltage, so we can actually just adjust the voltage to control the speed of the water flow. And because it pushes water with a piston, so the speed of the liquid is actually very unstable. So we also add a buffer, which is the silver tank. Actually, it's not made of silver, it just looks silver, it's actually just metal. And to let the water flow be more stable. And after acquiring the data, we uploaded the data into a MATLAB program and plotted the graph. Here's the graph of the signals when there's 0 voltage in the water pump, which means that there's 0 water flow. This is the data, and as you can see, all the 3 signals are perfectly overlapping each other. And because the driver's signal is a perfect sine wave, we can also say that the signals from the sensor are also sine waves, as they are perfectly overlapping. Then we changed the 0 voltage to 7 volt, and the graph is not bad. And then we changed to 10 volts, and the graph is a bit distorted, but still intact. Then 13 volts, still not bad. 16 volts, and the distortion begins to be quite clear. And finally, 19 volts. The distortion is now very obvious, but I hope we can cope with it. And here's all the data that we got. The first 3 columns represent the 3 times that we measured in each situation. And the average column is just the average of the 3 data on the left-hand side of it. And then there's the phase change, and it's calculated through the difference between the average of that row and the average of the first row. You take the difference and record it in the phase change column. And then there's the flow rate, which is measured through a quite cheap flow meter. And then there's a pressure inside, and finally the voltage at which the pump is working. And then we compare the data. Well, theoretically, the flow rate and the phase change should be proportional, so the graph should be in a linear shape. However, the graph is actually a curve, so one of the reasons, and it's just a hypothesis, It's probably because uh, our measure of flow rate is measured through a very cheap flow meter. So well, I guess it might not be very accurate. Maybe it's one of the reasons, but I'm not quite sure. I still didn't find out about it yet. And then here's the graph of voltage versus phase change. And the first segment of the graph is actually not a part of measurement, so let's just ignore it for the present being. And then after that, the graph is quite linear, which is a very good sign. But if you elongate the line backward, you'll see that it does not start from 0 point. And the reason for that is that the pump actually have a starting voltage, so unless you pass the threshold, or the pump won't start working. So I guess that's the reason why it does not start from 0. And finally, this is the graph of pressure versus phase change. And as you can see, the graph is quite linear. And well, I added an orange line to show exactly how linear it looks. It actually represents that the resistance to the flow is actually a constant throughout the experiment. It's just like Ohm's law, and you have voltage and current, and if the resistance is a constant, then the V and I would be proportional to each other. To summarize, because we have already got a relationship between the pressure and phase change, and it's quite linear, so I think our experiment is right now at a success. Our next step, technically speaking, should be precise calibration. And an easy way to do it is to do it with a balancing stopwatch. Just let the water flow for a specific amount of time, and then calculate the mass that has flowed through it, and see if it is actually the actual mass. But it's actually quite boring, so I might not do it. Yeah, unless I'm really bored, of course. So our next step would be trying to make 1 millimeter low flow rate measurement. Well, so this means that our next project would be really, really small. I mean, the tube is only 1 millimeter in diameter, which is a lot smaller than the mass flowmeter tube that we are using right now. But here's a question. Where do you think we can get a speaker of this size? And here's a hint. Can you guess where did I get this speaker? Well, if you think you have an idea, please add a comment in the comment section, and I'll try my best to reply to it. And finally, I will end the video with water sprays from a tube that is only 0.3 millimeter in diameter. Well, thanks for watching. Bye bye.